Everyone, in this video we are going to talk about Rademacher complexity. So look at this picture. The smooth can curve is the true signal. The jagged magenta lines is pure noise. So the model that can follow the noise perfectly has high capacity. The model that stay close to the smooth curve have low capacity. And the Rademacher complexity measures exactly how well a function class can fit pure random noise. That is the capacity we must control if we want the model to generalize. Then moving on forward, see, panel A shows a flexible class that can perfectly match random plus one or minus one labels. Its rate matcher complexity is high and it will overfit. Then second, panel B, like this shows a constraint class that cannot follow the random labels. Its rate matcher complexity is low, so it will generalize better. So if a class can fit noise, it may also fit the noise by that is already present in our training data, right? So now we see a formal definition of rate matcher. The empirical rate matcher complexity is an expectation over the random signs. We draw independent random signs like sigma that is equals to plus 1 or minus 1 with equal probability. So for each possible noise pattern, we find the function in class that correlates best with that noise. So then we average those best correlation, and that average is the capacity of the class to fit pure noise on the given sample. Now, we need to know about generalization bound. The true risk is bounded by three terms: training error plus twice the Rademacher complexity plus a small confidence term that shrinks with sample size. So in plain language, we can say like true risk is less than equal to what you see on the training set. Okay, and like it is how much your model can fake success by fitting noise, and second, ordinary statistical doubt. So these three things we can say. Then comparison with the VC dimension. So VC dimension is a combinatorial and what we can say and distribution free. So it often produces loose bounds that grow with dimensions. Rate matcher complexity is data dependent. So it produces tighter, often dimension free bounds that scale like 1 over square root of n. So in a concrete example with 1000 features and 1000 samples, the VC bound was useless. So while the rate masher bound was about 0.03, 40 times like tighter than that, right? Then there comes symmetrization proof. So the key technical step is symmetrization. So we introduce a second independent ghost sample because both samples come from the same distribution. Swapping a point between them does not change the overall law. So the random swaps introduce the rate matcher signs. The gap between the true and empirical risk is then controlled by the expected supremum of the correlation with those signs. Now here we see contraction lemma. So when we compose a function that class with the Lipschitz laws, the rate matcher complexity is multiplied by the Lipschitz constant. So this is why SVMs use the hinge loss. The 0 and 1 loss is not Lipschitz. So, but the hinge loss is 1 Lipschitz. Okay. Then the contraction lemma therefore gives clean bound that still controls the true 0 or 1 error. Then we see linear classifier. For linear classifier whose weight vectors have bounded Euclidean normalization, like wait, the rate matcher complexity is at most like b and c over square root of n. So notice what is missing, the ambient dimension. The bound depends only on the norm of the weights and the norm of the data. That is how we break the dimension barrier that plagued the VC theory. Now, classical parameters counting predicts the large network should overfit badly, and Rademacher analysis shows that the relevant quantity is the product of the layer-wise weight norms, not the total number of parameters. So, weight decay, which we can say L2 regularization, shrinks those norms and therefore shrinks the Rademacher complexity. That is why weight decay controls generalization even when network has millions of parameters. Okay, at the complexity spectrum. So at one extreme, Constant function have Rademacher complexity 0. They cannot fit any noise. And at other extreme, the class of all plus 1 minus 1 functions has complexity 1. It can fit any noise. So in between we find the threshold, linear classifiers, polynomials and neural networks, each with its own scaling. And the spectrum makes the relative capacity of different models families visible at a single glance. Now, local Rademacher complexity. So, global Rademacher complexity look at the worst case function in the entire class. That is often pessimistic. Local Rademacher complexity restricts attention to the function that are already close to the empirical minimizer. Finding the fixed point on the local complexity yields the rates that can be as fast as 1 by n instead of 1 over square root of n. Okay. Now we see some common pitfalls. So do not confuse the complexity of classifiers with the complexity of the composed local loss class. And the second is like the bound is uniform over the whole class, not only for the single empirical risk minimizer. Third is the Lipschitz constant multiplies the outer loss, not the inner function class. And next fourth is like the empirical Rademacher complexity is random and data dependent. So the population version is its expectations. Then okay, so Rademacher complexity appears in many modern arguments, like large margins produce smaller Rademacher complexity. That is the heart of the margin theory of the support vector machines. Then PAC base bounds becomes tighter when the posterior stay close to a diffuse prior, explaining why flat minima generalize. Then spectral normalization in GANs explicitly caps the Lipschitz constant of each layer and therefore throttles the Rademacher complexities. So Rademacher complexity in simply if we just take a summary. So Rademacher complexity measures a model's capacity to fit pure random noise. It is data dependent and often dimension free, giving tighter bounds than classical VC theory. For neural networks, the controlling quantity is the product of layer norms, not the parameter count. And even these tighter bounds are still too loose to fully explain the success of deep learning. Structure, the implicit bias of SGD, and sharpness remain active research topics. So that's all for this video. Hope you understood it. With this, we have finished our probability playlist. And if I found any more topics and any more interesting things in this, I will just make video over it and add on this playlist. So that's all for this video. Hope you liked it. Thank you for watching. Bye bye.